So today we are starting a new lecture series within the same optimization theme, and this is going to be on constraint optimization methods. So we'll spend the first few lectures discussing linear programming, and again this is lecture 28 on linear programming, and I am Dr. Ranjan Ganguly. Now, the so-called linear programs which constitute the subject we study under linear programming show up in a variety of fields. For example, in water resources, systems, traffic flow control, management of resources, transportation problems, electrical engineering, to name a few. Now, all these type of fields have a problem of giving certain resources to certain systems. So it's kind of a distribution problem in many cases. And linear programming is a very important field when you deal with some of these problems. Now, typically in optimization, as it's taught in most engineering domains, linear programming is given less importance, but I think that's not proper because linear programming is a bedrock for grasping the different optimization methods. We will also see that linear programs are an important part of a field known as OR. And this field is very important in business management. So again, people who are interested in the business side of the equation, they often study the field of OR. Now, like I mentioned before, in many of the typical mechanical engineering type of fields, most of the problems we deal with are nonlinear because we have objective functions such as weight, flutter, strength, and we have constraints on failure theories and so on. And these are typically governed by nonlinear functions of the design variables. In business, many problems are linear. For example, you have the well-known profit maximization problem, which is frequently discussed in linear programming. And these problems essentially require maximization of a cost function. So in these cases, linear programming becomes useful. Also, we will see that linear programming is important for a complete study of optimization. So if you are claiming that you know about optimization, you should know the basics of linear programming. There are also methods such as sequential linear programming, where you take a nonlinear optimization problem and you transform it into a sequence of linear programming problems. So again, here you can see that the software developed for linear programs can be immediately used in these situations. There is also a particular type of nonlinear programming problem known as quadratic programming, and these can be solved by the modified simplex method, which is typically developed for linear programs. Now, you could solve linear programs using general optimization problems, but there are some issues which come up. One of them is that as far as the objective function is concerned, if you consider any linear function, by itself it doesn't have a minimum point. It has a minimum point if you bracket it through some constraints. So it is sometimes better to use the concept of linearity, and therefore the methods which are used in linear programming could be called as methods which are based more in matrix theory than in calculus. So the methods which have been developed for solving the linear programs typically exploit the linearity of the problem and the fact that linear programs have linear objective functions and linear constraints. Linear programming problems also typically have different definition and nomenclature compared to the nonlinear programming problems. And this is partly because they have developed differently They do not use the calculus-based thinking which we have used in typical nonlinear programming of gradient vectors and so on. And therefore the concept is somewhat different. Now let us start creating the standard linear program. So let us start with the constraints here. So let us say we are at constraint number I, and essentially you have a linear constraint by definition, and it can be an inequality constraint or an equality constraint involving k design variables. So yj, j is 1, 2 all the way to k. So like I mentioned here, some of the nomenclature is going to change compared to the nonlinear programs we have discussed previously. So just keep that in mind. So now a constraint is given by this equation of a straight line or a plane. So you have ai1 y1 plus ai2 y2 all the way to aik yk, and you can have three possibilities. It can be equal to bi, it can be less than equal to, or it can be greater than equal to. And here aij, and bi are known constants. So this is a typical constraint for a linear program. Now this right hand side bi is known as the resource limit, and the requirement is that this must be non-negative, or bi is greater than equal to 0. Now here you can see that if you have the inequality constraints, you don't put them in the less than form as was done for the standard optimization problem in the nonlinear case. And this will become clear through an example. If you consider a particular system such as here 3y1 plus 2y2 is greater than equal to 5, you could multiply both sides by -1 to put it in the less than form. But immediately you see that the bi has become -5, which is not permitted because bi must be greater than equal to 0. Similarly, if you were to consider a situation like this, 3y1 plus 2y2 is less than equal to -7, and you try to remove this -7 here and make it positive, you would multiply both sides by -1. But then this would make the particular sign greater than equal to, and this would be required if bi is greater than equal to 0. So essentially the constraints in the linear program have to be greater than equal to, less than equal to, or equal to constraints. So all these three have to be permitted in any linear program, in contrast to constraints in a nonlinear program. Now, what do we do when we have the inequality constraints? Well, very similar to what we did in optimization for nonlinear problems, we convert them to equality constraints by putting something known as a slack variable. So if it is a less than sign, we can add si here, and this would become an equality constraint. Now, if it is a greater than sign, then we subtract si here, and this is known as a surplus variable. So now you have two variables here. You have the slack variable and you also have the surplus variable. Now by introducing this slack variable or surplus variable, you do create new variables in the problem, which essentially become the design variables of the problem for which you need to solve. So these are extra variables which you need to solve during the solution process. Now, if you go back to our previous methods where we used the KKT conditions on the nonlinear objective function and constraints, we used SI square as the slack variable, and doing this SI square enforced the fact that SI square was greater than equal to 0. Now in nonlinear programming, we cannot add anything like SI square because that would make the problem nonlinear, because SI square is a nonlinear function. Therefore, what you need to do is introduce some constraint like Si greater than equal to 0, and this is required for both slack and surplus variables, and this new constraint essentially takes care of the fact that Si is greater than 0 directly. Now, one more requirement for a standard linear program is that all design variables must be non-negative. That is why I is greater than equal to 0, I is 1 to k. Recall that there are k design variables for this problem. Now, this seems an odd requirement because in a practical problem, you have the possibility that your design variable can be positive or negative. So which we shall call as unrestricted or free in sign. So this is typical. Now there is a mathematical subterfuge you can use to counter this problem, and this would be by expressing the unrestricted design variable as a difference of two non-negative variables. So I can write yj equals to yj plus minus yj minus, where both this yj plus and yj minus are always greater than equal to 0. And then you can substitute this in the linear program and then solve the linear program, because now the design variables satisfy this particular constraint of being greater than equal to 0. So if you consider the possibilities, if you are at a particular optimal point, if yj plus is greater than equal to yj minus, then yj is non-negative. If yj plus is less than equal to yj minus, then yj is non-positive. So both these possibilities in terms of the unrestricted design variables are taken care of by permitting yj plus and yj minus to be both positive. So this essentially solves the problem of negativity in the design variables. But whenever you have any of these free design variables, which essentially means they are free in sign, they do increase the number of design variables by 1. So this is a place where your problem size increases. So now that we have defined the basic concept about how a constraint should be framed in the LP problem, let us add the objective function to the constraints and define the standard LP problem. So like I have mentioned before, the function as far as the objective function is concerned plays a role in LP as long as constraints are there, or it's simply a straight line or a plane with no minimum. So now let us define the standard linear program. Let x be a vector of size n with k design variables with which you started with, and n minus k slack, surplus, and further variables. Now these are introduced because of the free signs and so on. Now you need to find this x to minimize the objective function given by fx equals c1x1 plus c2x2 plus c3x3 plus cnxn. So now we are back to our familiar nomenclature of n design variables, while keeping in mind that this n now includes these particular slack, surplus, and different variables. Now this objective function by itself would not really have a minimum. So you can see that this is essentially a line which has a slope, and therefore it would keep going down, down, down like that. You can picturize it as a plane. If you want to use gradient based thinking here, if you were to take the gradient vector of this function, you would get essentially, say, df by dx1 would be c1, df by dx2 would be c2, like that. And if you set that all equal to 0, essentially all these would become 0, and therefore you would have no function in the first place. So that is a problem with using gradient thinking here. Now if you look at the constraints, again you have a set of lines here, but you have m equality constraints. And recall that I have converted all the constraints to this equality form by adding slack or surplus variables, which are of course always positive. So therefore these slack and surplus variables are now part of this X system. So first x1 to xk would be the design variables with which you started the problem, and beyond that xk plus 1 to n would be all the slack and surplus variables and the variables which have come because of the free sign. So this particular system of equations constitutes your constraints, and essentially this is what bounds this particular line, and therefore this line is going to cut this system somewhere, and that is going to give us some concept about where the optimum point may lie for this particular problem. Now the design variables are all non-negative, which is a way of saying they are greater than equal to 0. J is 1, 2, all the way to n. So this particular definition constitutes the typical standard linear program. Now the next thing we are going to do is to write this in matrix form, because we don't want to keep writing this cumbersome notation for every problem. So we'll do that. So essentially this is the matrix form of the standard LP. Fx is C transpose X subject to the linear system Ax equal B and X is greater than equal to 0. Now if you think about these matrices, A is an M by N matrix. X and C are n by 1 vectors and B is an m by 1 vector. So these essentially constitute the vectors and matrices in the linear program. The problem is completely defined by matrices and vectors. Now the quantities Bi must be greater than equal to 0. Cj and Aij, these are the known constants for the problem. So once you have defined a particular problem to solve certain realistic problem, you have to express this in the standard LP form, and then we can go ahead and use some of the methods we are going to discuss later in this lecture series to solve this particular problem. So very important to remember that the standard LP can be expressed in a matrix form, and therefore essentially it becomes a matrix theory type of problem. Minimize this particular function subject to this linear system and x greater than equal to 0. So we will see that the constraint set here will play a very important part in solution of this particular optimization problem, because the constraint set essentially dictates where the optimal solution is going to lie. So that is something which is very important, and that is why it's a good idea to begin constraint optimization with linear programs, because you will start getting a good feel about the constraint space and its impact on the optimization problem. So we will end this lecture here, and in the next few lectures we are going to delve deeply into the linear programs and their solution. I'll see you in the next video.